Greetings, Mr. Perry here, and we're going to take a look at part 2 of Forces and the Universe. Ms. Vondriska has some good information for you here. We're going to look at, in this unit, gravity, electrical, magnetic, and wave energy forces. Let's do a quick review. Previously, we covered energy as waves. Longitudinal compression waves is energy carried through compressions, which is squeezing together, and rarefactions, which is stretching out of a substance like air or water. The slinky in the diagram moves back and forth, carrying its energy through compressions or squeezing and rarefactions, which is stretching. Also in energy as waves, we have transverse waves. Substances moving up and down in S-shaped waves carry energy forward at right angles, which is transverse to the direction of the S-shaped movement. The slinky is moving up and down in an S shape, but the energy is traveling forward at right angles to the S-shaped waves. With that, let's take a move forward and look at mechanical waves, seismic. Seismic waves, stored energy in rock deep inside the Earth that is suddenly released and travels as compression and S waves through rock faults, and they come up through the Earth's surface. As the wave travels, it produces violent shaking of the ground and an earthquake. The largest earthquakes can release as much energy as a small atomic bomb, and faults are cracks and weaknesses in the Earth's rock. Also, in the seismic realm, we have primary or P waves, or seismic earthquake waves that are longitudinal compression waves that can travel through solids and liquids. They cause damage by pushing and pulling things back and forth in the same direction that the wave travels. Now, P waves move extremely quickly through the Earth's interior at a speed of about 25,000 kilometers per hour, which is roughly 15,500 miles per hour. And we have secondary waves, or S waves. They are transverse seismic waves that come after P waves and travel through solids only. Now, S waves shake rocks up and down or from side to side as they move forward, which causes a twisting or shearing motion. S waves also travel through the Earth's interior, but at about half the speed of P waves. Now, earthquakes kill around 10,000 people every year worldwide, and many cities now have buildings that absorb the energy that is produced by seismic waves. They may wobble, but they don't collapse. Let's check this out.
What I'm going to represent is an earthquake. So I'm standing on the surface of the Earth, and in class we talked about the whole idea that there's this idea of the fault. So we can assume that the fault is relatively shallow compared to the length of the Earth. And so even though I'm not going to have the fault starting down here, the earthquake is going to start on the surface of the Earth and it's going to travel through the substance. Okay, so here's how this works. So P waves, who can remind me what's important about P waves? What did we just learn? Two things.
They're fast.
They're fast, and number two,
They go through solids and
they go through solids and liquids. So this, and P waves, and the other thing that we're going to add to those notes that we took in class is that they bump into the thing next to them. So this is how it travels. So here's a P wave. I'm going to simulate an earthquake by pushing the ground. And this is how a P wave travels. It bumps into the thing next to it. Watch it one more time. Just look at the rings of the slinky. What happens to the rings of the slinky as I have the earthquake? I know you're about to raise your hand.
yeah, they're like together.
Bingo. They get closer together. Everybody see that? Okay, watch this one more time. Watch how the rings get closer together. Okay, so they bunch, and then that bunch of coils just kind of moves. That bunching kind of moves all the way down. And if it hits something else, it bounces back. Now S waves are a little different. they move in a side-to-side motion. So to model how an S wave travels with the slinky, what I'm actually going to do is just take the earthquake and it's going to model a side-to-side motion. Now watch how the slinky moves. And here it is. Okay, so you guys see how it kind of moves side to side? So it's very different. Now if there's a bit more energy to it, it'll bounce back as well. Okay? Okay. So, do you think this slinky is modeling solids, liquids, or both? Dylan, what do you think? Solids, liquids, both? Solids. Okay, good. It's solid. So this is measuring solids. Okay? So, because S waves don't travel through liquids, right? So all models work to a certain extent. At some point, the model doesn't work exactly like it's supposed to. And that happens with every model, okay? And this is no different. So here we have a model of seismic waves of how they travel through the material using a slinky. Slinky is very commonly used, but it has some limitations to it. So P waves are the fastest, right? We learned that in class. So I want you to kind of compare the speed between a P wave and an S wave, all right? So here's my P wave. Just watch how fast it moves through the material. Do it one more time. All right, so there's our P wave. Now, S wave. Side to side, watch how fast it goes. Okay, so which one went back and forth way more times? S waves, right? Now, S waves are supposed to happen slower. Do you see a distinctive difference in speed between P waves and S waves?
Yeah.
Which one do you think happens faster?
P waves.
Ah, how many people think P waves happen faster? According to this link, how many people think S waves travel faster? Okay. We know on the Earth that P waves travel faster. So I want you to think about this. Why does the model with the slinky not quite show that? And I just want you to think about one word, friction. What is it about the friction of the slinky that makes it not work the way it's supposed to? Go ahead and talk really quick to the person next to you. Okay. Anyone willing to give me what you got? Quentin?
So when it's going that way, it's got more friction because these are flat and not facing that way.
Okay.
But when it's going this way, it's like flat, and
But-
it's easier to go back.
All right, very good. So if you were to look at the coil of the slinky, it has to do with how the slinky is shaped. So here we have this really thin edge, and the thin edge moving back and forth like this, there's not a lot of friction. It's this little tiny thin edge moving back and forth. But if you take that thin edge and try to push it against the floor in the opposite direction, there's way more friction in that. And so even though the P wave, if we were to measure the P waves traveling through the Earth, they go way faster than S waves. But because of the friction of the slinky with the floor, it actually does not appear that way. Questions on that?
So there you have it, Forces and the Universe, Part 2. This was Segment 2, Slides 9 through 11. And in this series, we'll be covering gravity, electrical, magnetic, and wave energy forces. So until next time, may the force be with you.